What is stoichiometry? Stoichiometry is, for some chemical reaction, you're quantitatively analyzing the amounts of the substances, of the reactants or products involved in the chemical reaction. Okay, so let's say you have some chemical reaction that you want to analyze, and so you start by constructing the corresponding chemical equation for that chemical reaction. You account for all of the reactant compounds involved and all of the product compounds involved. Then you list all the reactant compounds on one side of an arrow, and you list all of the product compounds on the other side of the arrow. Then you balance the chemical equation, right? So let's say we're analyzing the chemical reaction. You have solid sulfur reacting with oxygen gas to produce sulfur dioxide gas. Okay, so you write out all of the reactants, all the products, and balance the equation, and here's the balanced chemical equation. Okay, and so when performing stoichiometry, again, you're analyzing amounts of any of these compounds involved in the chemical reaction. For a given amount of solid sulfur, how much of that sulfur is going to react with oxygen gas? How much oxygen gas is it going to react with? For a given amount of solid sulfur, how much sulfur dioxide gas will be produced? Or if I want to produce a certain amount of sulfur dioxide gas, how much oxygen gas will be needed? Or how much solid sulfur will be needed? That's stoichiometry. Again, stoichiometry is a quantitative analysis of the amounts of substances involved in a chemical reaction from any perspective you want, from the perspective of any of the reactant compounds or any of the product compounds. Okay, so the first thing to note is that I've used the word amount, the amount of products or reactants involved in a chemical reaction. So what is the meaning of the word amount when referring to a specific compound or substance? The amount of S8, sulfur, the amount of oxygen gas. Well, this could be a count. So a certain number of O2 molecules reacting with a certain number of S8 molecules. Those are amounts, right? But you could also describe the amount of a substance from the perspective of mass or weight. So a certain mass of sulfur dioxide gas, maybe in AMU or maybe in grams. If I want to produce 25 grams of sulfur dioxide, how many grams of O2 gas is needed? And how many grams of solid sulfur, S8 sulfur, is needed? To describe the amount of substance, you also could use volume, right? A certain volume of oxygen gas, a certain volume of sulfur dioxide gas, a certain volume of sulfur. Okay, but now stoichiometry is performed. The heart of stoichiometry is based on what's called the mole method, to where the mole method is just saying how you can interpret any balanced chemical equation from the perspective of moles of substances. So you could say 1 mole of S8 reacts with 8 moles of O2 to produce 8 moles of SO2. So to understand how stoichiometry works, it's important to first be very clear on why interpreting any balanced chemical equation from the perspective of moles makes complete sense. Okay, so the reason why this makes sense is that we know that chemical equations, a chemical equation like this, any balanced chemical equation, fundamentally, what the equation is expressing is it's expressing to you what exactly is taking place at the molecular level, at the atomic level, on a molecule by molecule basis or an atom by atom basis, right? So we can really fundamentally interpret this chemical equation here, for example, as you have an S8 molecule, a single S8 molecule interacts with 8 O2 molecules to produce 8 SO2 molecules. That's really the fundamental way to understand any chemical equation. right? So we can look at this visually. You have a single S8 molecule with 8 sulfur atoms. This interacts with 8 O2 molecules. Then the chemical reaction takes place. Bonds are broken, atoms get rearranged, and what's produced is these 8 SO2 molecules. These 8 sulfur atoms are all accounted for, and these 16 oxygen atoms are all still there. The chemical reaction took place, and you got this new chemical compound. Okay, but interpreting this chemical reaction from a mole perspective, so saying 1 mole of S8 reacts with 8 moles of O2 to produce 8 moles of SO2, is still the exact same concept as looking at this reaction from this perspective, at as close to a molecule by molecule perspective as possible. Because from the mole perspective, all we've done is just scale everything up. That's it. That's all we've done. What I mean is, so remember, the mole is just a scaling factor in the exact same way that a dozen is just a scaling factor. So would it make sense to read this chemical equation this way? What if I said that 1 dozen S8 molecules react with 8 dozen O2 molecules to produce 8 dozen SO2 molecules? Well, of course that makes sense. Yeah, you're just saying, okay, you've got 12 of these, and then just to not change the proportions, that's all that matters, you need to multiply this by 12. So 12 times 8, you'd have 96 of these, and then you're going to produce 96 of these. And in that case, everything still makes sense. You can account for all the sulfur atoms and all the oxygen atoms. You just scaled it up. Well, we've done the exact same thing with the mole, except instead of scaling up the entire equation by 12, we scaled it up by 6.022 times 10 to the 23rd. That's it. But scaling it up this much makes sense because for a general amount of oxygen gas that we'll have in a lab, a certain amount of grams or volume of oxygen gas, a certain number of grams of sulfur, we're going to be dealing with oxygen atoms, sulfur atoms. The total number of oxygen and sulfur atoms we're going to be dealing with in that case is going to be on the order of that times 10 to the 23rd, on the order of moles. So that's why it makes sense to scale it up that way. We're going to have, in the lab, we're going to have an extremely large times 10 to the 23rd order of oxygen molecules that we're dealing with. Okay, so again, this is really important to understand stoichiometry, just how it makes perfect sense, how you can visualize, describe any chemical equation, any balanced chemical equation from an atom by atom, molecule by molecule perspective. This 1 molecule of S8 reacts with 8 molecules of O2 to produce 8 molecules of SO2. We all know that makes perfect sense. Okay, it also makes perfect sense to just scale this up by a mole. We're still just dealing with counts if we say 1 mole of S8 reacts with 8 moles of O2 to produce 8 moles of SO2. That makes complete sense. Okay, now, but why is the foundation of stoichiometry, the heart of stoichiometry, based on what's called the mole method, based on interpreting a chemical equation on a mole basis, not an atomic basis? Well, the reason is because if we're going to be calculating quantities of reactants and products in a chemical reaction, well, in general, these quantities, in some respect, are going to be based on amounts of reactants we're bringing into the lab to run an experiment, to perform a chemical reaction. We purchase kilograms of oxygen gas. We purchase pounds of sulfur, right? In general, the quantities that are involved in chemical reactions of reactants and products are in some respect going to be related to masses that we measure on the human size scale. Grams, kilograms, pounds mass. Okay, and as we know, the direct link of these human size scale quantities, like grams, kilograms, to the atomic world, atomic masses and counts, is through the mole, Avogadro's number. So that's why stoichiometry, the heart of stoichiometry, is from the perspective of the mole. Looking at a chemical equation in terms of moles of atoms and molecules reacting and being produced. Okay, now, so using the mole method for any balanced chemical equation, all of the reactants and products, they're all what's called stoichiometrically equivalent to one another. So for this equation, for example, 1 mole of S8 is stoichiometrically equivalent to, and I can pick any of the other substances, the O2 or the SO2. So let's say 8 moles of SO2. Or I could say 1 mole of S8 is stoichiometrically equivalent to 8 moles of O2. But you could state this in reverse as well, that 8 moles of O2 is stoichiometrically equivalent to 1 mole of S8, right? Like an equality goes in both directions. With the stoichiometric equivalency just meaning that it's not an actual equality, it's just this equality that applies to the quantities associated with a chemical reaction. Outside of the context of this chemical reaction, you can't just make an arbitrary statement that a mole of S8 is the same thing as 8 moles of SO2. It's just this, in the context of this chemical equation, for performing stoichiometry, 1 mole of S8 is stoichiometrically equivalent to 8 moles of SO2. Okay, and so again, for any balanced chemical equation, no matter how many reactants and products there are, from the mole perspective, everything is stoichiometrically equivalent to everything. 8 moles of HNO3 is stoichiometrically equivalent to 2 moles of NO. You could say that in reverse as well, that 2 moles of NO is stoichiometrically equivalent to 8 moles of HNO3. Or 4 moles of H2O is stoichiometrically equivalent to 3 moles of copper. 3 moles of copper nitrate is stoichiometrically equivalent to 4 moles of H2O. Everything is stoichiometrically equivalent to everything once the equation is balanced from the perspective of moles. So what does this mean, though? What does stoichiometrically equivalent mean? Okay, well, these equivalencies are just sort of formally making the same statement that was made when I originally read this equation from the atom perspective or the mole perspective, right? That you have 1 mole or molecule of S8 reacts with 8 molecules or moles of O2 to produce 8 molecules or moles of SO2. These stoichiometric equivalencies are just from a formal mathematical perspective telling you that, so, okay, for every 8 moles of HNO3 consumed in this reaction, 2 moles of NO gas are produced. Or for every 2 moles of NO gas produced, 4 moles of H2O liquid are produced. Or for every 3 moles of solid copper consumed with the reactants, 3 moles of copper nitrate are produced. Copper 2 nitrate. That's it. That's it. Now, you might be saying, well, why do these stoichiometric equivalencies have to be stated in terms of moles? Well, technically they don't. It is absolutely true that if you said 1 dozen S8 molecules is stoichiometrically equivalent to 8 dozen SO2 molecules. That's correct. Or just 8 O2 molecules are stoichiometrically equivalent to 1 S8 molecule. That's correct because, yeah, for every 8 O2 molecules that are consumed in this reaction, 1 S8 molecule is consumed. Or you could say that from the perspective of dozens. However, the stoichiometric equivalencies are more formally stated in terms of moles because, again, this is we look at stoichiometry, the foundation of it is from the perspective of moles. To move from grams or any human mass, human size scale amount to the atomic world, we're going to need to convert to grams. And then from grams, we can get to moles using Avogadro's number, right? Even if we're dealing with volumes, like a certain amount of substance in volumes, well, if we have the density of that substance at a certain temperature, that's mass per volume, then since we have the volume, we can get the mass. And no matter what the mass units are, if we have the quantity of mass, we can convert that to grams easily. Okay, but why do we need the stoichiometric equivalencies? What's the purpose of these equivalencies? Well, their purpose is because for general real-life circumstances, when we're analyzing chemical reactions, the amounts of substances involved in chemical reactions, the majority of the time, we're not going to be dealing with perfect stoichiometric amounts of reactants or products. For example, like if we asked the question, for exactly 8 moles of oxygen gas, or maybe some nice multiple of 8, exactly 16 moles of oxygen gas, how many moles of S8 sulfur are consumed and sulfur dioxide are produced? Right? This nice, perfect stoichiometric amount. That's a clean multiple of one of these coefficients. No, that's not how real life situations work, right? We could have some random number of moles of O2 or S8. If we have 12.2 moles of O2 gas to start with, then how many moles of S8 is that going to react with? And how many moles of SO2 will that produce? Right? So with these non-stoichiometric amounts, we're going to need the stoichiometric equivalencies. We're going to need to use these equivalencies as conversion factors, as like stoichiometric conversion factors. So a conversion factor, it's like if you're saying, okay, 1 foot is equal to 12 inches. This is not a stoichiometric equivalency. This is an actual equivalency that applies universally in all contexts. But okay, if you're saying, okay, I have 144 inches, how many feet is this? Well, you convert. You say, okay, there's 12 inches in 1 foot. Now you're in feet. 144 divided by 12 feet. But you can go the other direction. You could say, if I've got 32 feet, how many inches is this? Then you say, okay, there's 12 inches in 1 foot. The feet cancel. 32 times 12 inches. You're going to use the stoichiometric equivalencies in the same way, just when doing stoichiometry. So, for example, if the question was, if I'm going to start with 12.2 moles of O2 gas, so 12.2 moles of O2, then, you could ask any question, how many moles of S8 will that react with, or SO2 will that react with, or will be produced? Well, okay, you just use the stoichiometric equivalency that applies to the question that's being asked. If you're being asked about the S8, then you need to use the equivalency that 8 moles of O2 is stoichiometrically equivalent to 1 mole of S8. So then you just say, okay, you want the moles of O2 to cancel, so 8 moles of O2, 1 mole of S8, and there you go. But you could have done the same thing if the question was about how much product is produced. So you would 1.525. So if you started with 12.2 moles of O2, you would need 1.525 moles of S8 to fully react with all of those moles of O2. And again, how many moles of SO2 would be produced from this 12.2 moles of O2 or 1.525 moles of S8? You could just do another calculation with a stoichiometric equivalency that includes SO2. Okay, but now, what if you're dealing with a quantity of reactant or product that's a human size scale quantity, like grams or pounds mass or tons? If I'm starting with this many grams of O2 gas or this many pounds of sulfur, S8, how many corresponding grams or pounds of O2 is needed to fully react with the sulfur? And then how many grams of SO2 or pounds of SO2 will be produced? Or you could, from the beginning, be looking at this from the perspective of the products. If I want to produce a certain amount of product in grams or pounds, then how much reactant am I going to need? Okay, well, this is really simple because, first of all, remember, if you have a quantity of some substance, any substance, If you know its mass in any unit of mass, or even its volume in any unit of volume, but then with the volume you have a density value to where you can determine from the density and the volume what the mass is. So you ultimately have a mass in any quantity of mass, right? Well, it's easy to convert quantities to any unit you want. I mean, just look at Google, for example, right? They give you all the main mass units. You can convert to whatever you want. Now, you should know how to do the conversion yourself, but I'm just pointing out that it's easy to convert units once you already know or you have the quantity. Okay, so what you're going to do is you're just going to take those masses and get them to grams. Get everything converted to grams. Why? Why grams? Because that's your bridge to the mole, either to the atomic level or out of the atomic level, depending on the direction you're going. And for any given stoichiometry problem, you're going to be going in both directions, to the atomic size scale and then back out. Why? Because like the idea is you're going to have some information, quantity, amount information about a certain reactant or product. You're going to convert to grams, then to moles. And now once you're in moles, you can use stoichiometric equivalencies to switch to any other reactant or product you want, right? Okay, and now that you have that other reactant or product in moles, now you can go back out. Go back out to grams and then convert from grams to any mass unit you want. That's the idea. Okay, so like for example, let's say you're going to start off with 20 pounds of copper, pounds mass of copper. And then you could be asking any question about, well, how many pounds or whatever, grams, kilograms of HNO3 is this 20 pounds going to react with to have a complete reaction? Or how many pounds or grams of nitrogen oxide are going to be produced from this 20 pounds of copper? You could be asking anything. But what you're going to do is you're going to start here. Then if you want to get to some other substance, you're going to need to get to moles. So you can apply the mole method. Use the stoichiometric equivalencies. So you're going to say, okay, well, 20 pounds mass is how many grams? Okay. $9,072 grams. So you got okay, but we need to be in moles. How do you go from grams of a substance to the number of moles of that substance, the count of the particles of that substance? You use the molar mass, grams per mole, right? Which corresponds to the mass of a single copper atom in AMU. Okay, 63.546. So there's, if you have 63.546 grams of copper, then you know that there's approximately 1 mole of copper atoms. All right, these cancel. Now we're in counts. Now we're in counts of atoms. Now we can move anywhere we want to any other substance within this chemical equation. So if we're thinking about if this 20 pounds mass of copper fully reacts, it all reacts, then how many, let's say, kilograms of NO are produced? Well, okay, to get from copper to NO, we need to use the stoichiometric equivalency. Well, we're in moles of copper, so now we can apply the equivalency. The equivalency is for every 3 moles of copper consumed in this reaction, 2 moles of NO are produced. Now we're in moles of NO. Okay, but now we want to get back out of the atomic level, back to the macro level, with grams and pounds mass. Well, we're in moles, so we just need to use the molar mass. Okay, well, what's the molar mass of an NO molecule? That's going to be the molecular mass. It's the same quantity as the molecular mass. So the atomic weight of a nitrogen plus the atomic weight of an oxygen. 30. So for every 30 grams of NO, there's 1 mole of NO molecules. So now if we multiply all of this, 9,072 times 2 times 30 divided by 63.54 divided by 3, the result is grams of NO, which is it's just telling you that if 20 pounds mass of copper is fully consumed in this reaction, then 30 grams of nitric oxide gas are going to be produced. But again, now that you have this mass in grams, you can convert it to whatever you want. So in kilograms, you're just going to do, okay, you just add, there's 1,000 grams for every 1 kilogram. You're just going to divide by 1,000. Now you're in kilograms. Or you could convert this to anything, any of these mass units. Okay, but now, when doing stoichiometry, from a more general perspective, when working any stoichiometry problem, you're going to need to consider if one of the reactants is what's called a limiting reagent, and then which reactant is it? Okay, and all a limiting reagent is referring to is that, so again, from a more realistic perspective of actual chemical reactions, you're not dealing with these nice stoichiometric, these perfect stoichiometric amounts of reactants, right? You have exactly 8 moles of O2 you're starting with, or 16 moles of O2 you're starting with, right? In most circumstances, the idea is, so from the idea of a limiting reagent and excess reagents is strictly from the perspective of reactants. So focusing on all of the reactants, what's generally going to be the case is that you're going to have a certain amount of all of the reactants you're starting with, a certain amount of pounds of S8, a certain volume of O2 gas that you're starting with. And as a result, what happens is, as you're performing that reaction, you're going to run out of one of the reactants first, right? This is what's going to happen in most realistic circumstances. For realistic chemical reactions in the lab, in industry, you're most of the time, you're not going to have like the perfect stoichiometric amounts of all the reactants to where when the reaction is finished, everything is perfectly consumed. All the reactants are perfectly consumed. No. The reaction is going to stop and you're going to be left with excess reactant. That's what's going to happen most of the time, right? And so all the term limiting reagent is referring to is it's the reactant that runs out first and causes the entire reaction to stop, right? Because even if you have some big chemical reaction with 5 reactants, if one of those reactants gets completely used up, well, then the whole reaction can't continue, right? So the reactant that gets completely used up first is called the limiting reagent. Typically, you're going to have just one limiting reagent. One reactant is going to be the limiting reagent. But you could have a special case if you have multiple reactants that are present in the perfect stoichiometric amount and they both get used up at the exact same time. Well, then you have more than one limiting reagent. But in general, you're going to have one of the reactants is going to be the limiting reagent, and the rest of the reactants are going to be what's called the excess reagents. They're going to have excess material left over when the reaction stops. Okay, but now how do you determine which reactant is the limiting reagent? Well, you can just use your intuition to do this, right? The idea is you're going to have, again, we're just, with limiting reagent, we're just focusing on reactants in a chemical reaction. You're going to have quantity information, amount information about all of the reactants. So what you want to do is just convert those quantities to moles of the reactants, and now you're looking at it on a molecule by molecule basis, atom by atom basis, right? If you started off with 38 moles of O2 and 10 moles of S8, well, we can look at this from a molecule by molecule perspective. Same thing as moles. So, okay, 8 molecules of O2 get used. So now you have 30 molecules of O2, but only 1 molecule of S8 was consumed. Okay, now 8 more molecules of O2. 8 more molecules of O2. 8 more. Right? You can see the limiting reagent is going to be the O2. All or the majority of the O2 gas is going to get consumed, and you're going to be left with an excess of the sulfur. And so now the concept of theoretical yield with stoichiometry, with chemical reactions, you'll hear the term theoretical yield. all that's referring to is, so for any chemical reaction, when it comes to like theoretical yield and actual yield, we're really thinking about realistic, real-life chemical reactions. Okay, in general, you're going to have a limiting reagent and excess reagents, right? I mean, theoretical yield still applies if you don't have a limiting reagent. If you have a perfect stoichiometric amount, it still applies. But in general, you can think about you're going to have a limiting reagent and excess reagents. Okay, so you're going to run this chemical reaction in like an industrial process, and you know the starting amount of copper you're going to start with and the starting amount of nitric acid. So what you do is, on paper, you determine, okay, what's the limiting reagent? Which one of the reactants is the limiting reagent? Okay, once you figure that out, any stoichiometry you do is going to need to go through the limiting reagent quantity. You can't use the quantity of the excess reagent to do stoichiometry to calculate quantities of other reactants consumed or certain products produced. Why not? Because with the excess reagents, not all of that material reacted in the chemical reaction. You can't be doing stoichiometry with amounts of material that didn't take part in the reaction, right? And you know the reaction stopped when the limiting reagent was used up. So everything's going to go through the limiting reagent. And so the idea of theoretical yield is that you determine the limiting reagent, then you use stoichiometry going through that limiting reagent to calculate a certain quantity of a specific product produced. Whatever product is of interest to you, right? You might be trying to extract a mineral or gold or silver or something. What product is of interest to you? Okay, so the theoretical yield is, the idea is, if the reaction took place perfectly, all of the reactants were put in, the full amounts of reactants, then the limiting reagent was completely used up, and all of that limiting reagent and the rest of the reactants were stoichiometrically perfectly converted to what the stoichiometric calculation says the amount of the product of interest that should be coming out is. The amount of gold, the amount of nitric oxide gas. Okay, but we know in real life systems, the processes don't take place perfectly efficiently. In the vast majority of cases, what should be coming out theoretically, the theoretical yield of a certain product, which the theoretical yield was calculated from the hypothetical perfect stoichiometric amount being converted to product. You're never in actuality, once you get the actual product, collect it all, and go measure its mass, the vast majority of the time that the mass you measure is going to be less than what the theoretical yield value says it should be. And that's what's called the actual yield. And the percent yield is, you just take the actual yield and divide that by the theoretical yield, and then times 100%. Okay, so that's stoichiometry. That's a summary of the fundamentals of stoichiometry.